Next, I want to talk about air pressure. And air pressure is kind of the density of the air molecules. The closer you are to the Earth's surface, the more density of molecules you'll have, higher the pressure, and as you go further out, there's less dense. So you may have had I've had this happen where one of my kids had one of these kind of like a Gatorade bottle where when we drove into the mountains at a certain point, it actually squirted water out because of the change in air pressure going up the mountains. But probably in more practical terms, the way when we want to talk about air pressure is what we want to describe is the difference between what we call low pressure and high pressure systems. Because the unequal heating of the earth, in some places air is going to be rising, in some places the air is going to be descending. And where we have low pressure, the air is rising and it's kind of creating a vacuum. And where we have high pressure, the air is descending and it's creating a greater density of molecules. And so what winds are is they're responding to this, that they are moving of air from high pressure where there's extra molecules to low pressure where there's a less density of molecules. And so that's generally it's a three-dimensional system where air is moving upward and downward, and then also air is moving at the surface to fill in those gaps. By the way, one thing you should note up front, this is going to be a recurring theme, is that when air moves upward, you're going to get cloud formation and wet conditions. We're going to be discussing that more in the future. And where air is moving downward, it's actually heating up, and it's going to have more dry and sunny conditions. So in Fresno in the summer, we tend to have a high pressure system, which is why we're so generally cloudless and sunny. So I just want to talk about the movement of air just in general and some of the patterns. So this is what's called an isobar map, a type of isoline map with lines of equal air pressure. And here we have high pressure. The average for the Earth is somewhere around 1,000, just above that. And here we have high pressure, and here we have low pressure. And the idea is that winds would move from high pressure to the low pressure. So where we have high pressure, there's a greater density of air. Where we have low pressure, where it's moving up, we have lower density of air at the surface. And so winds are going to move and fill in the gap. Now, the reason for this, again, is because the Earth is not heated equally. And so winds are really a response to this unequal heating that kind of fill in these gaps. That might tell you why I usually record these at night when my dog's asleep, but excuse the dog there. But anyway, so air would move from high pressure to low pressure, but it doesn't go in a straight line. It actually goes in a curved direction. And let's talk about why that is. Okay, it has to do with something called the Coriolis effect. And this is due to the rotation. So if you can imagine, let's say you're Santa Claus and you're the substitute Santa Claus. You're not as experienced, and you want to fly your sleigh to New York City. And so you go into the upper atmosphere and you kind of point the sleigh in that direction. But you ended up instead in Chicago. So what happened while you were, flying your sleigh in that single straight direction? What happened is that the Earth is rotating underneath you. So while the sleigh itself maybe went in a straight direction, it would appear that it's in a curved direction. I'm going to post some videos that help illustrate this. It's kind of a confusing notion, but if you kind of watch those, I encourage you to, you'll kind of get a little bit of the physics behind it. It's not that the winds are not moving straight, it's just that on a rotating system, there's an apparent curve in that direction. And this is called the Coriolis effect. It's apparent from the observer deflection of the wind, and it's caused by the Earth's rotation. And it creates a pattern that in the northern hemisphere, winds are deflected to the right. And this sets up a clockwise pattern. If you recall, when we looked at ocean currents, they moved in a clockwise pattern because they were in the northern hemisphere because they're being pushed by these winds. In the southern hemisphere, the pattern is the opposite. Winds are deflected to the left. This creates a counterclockwise pattern. So know the difference that they're deflected to the right or clockwise in the northern hemisphere and to the left or counterclockwise in the southern hemisphere. Now, when you're right at the equator, there's no deflection. The winds just kind of move in a single direction. And we'll talk about that later when we get back to talking about hurricane formation, that type of thing, because it's this spinning pattern that you need for hurricanes to be created. So this is just a couple of figures showing from the North Pole, you'd be deflected to the right. Going California to Boston, you'd be deflected to the right. In the Southern Hemisphere, you'd be deflected to the left. And this is due to the Earth being a rotating system. So on a weather map, if you look at from high pressure to low pressure, rather than it being winds blowing in a straight line, they're going to be blowing out of a high pressure system in a clockwise direction. That's the wind patterns we see. And then they're going to be spinning into low pressure systems in a counterclockwise direction. Here's more of a 3D view. In a high pressure system, they're kind of spinning clockwise downward. And then the opposite is happening in a low pressure system where the air is moving upward. So rather than going straight up and straight down, they're kind of spinning downward or spinning upward. So if we didn't have Coriolis force, winds would blow in the straight direction from high pressure to low pressure, into low pressure, out of high pressure. One thing I'll point out too about winds is that you have more friction at the surface than you do in the upper atmosphere. So when you're really high in the atmosphere, there's no trees or rocks or things to kind of break up the air. So it moves at a very rapid speed because of the lack of friction. So winds in the high atmosphere actually are extremely curved. They move in a direction where they just kind of go round and round and round. When we look at winds like the polar easterly, it's called, it'll just be moving in a kind of a round and round direction. However, what we typically observe at the surface is that friction is slowing the wind some, so they move in this type of a pattern. From high pressure, they move curved to the right in the northern hemisphere and curved to the left in the southern hemisphere. And then the opposite is occurring as they go into a low pressure system. So the pattern, the low pressure pattern, is called a cyclone system. This is rising air that's here. Rising air is moving in what's called a cyclone, kind of like a hurricane does in a spinning direction. And then the opposite is called anticyclone. High pressure is moving downward in the opposite direction. This is the cyclone conditions are going to create dry conditions, and anticyclone or high pressure is going to create wet conditions. I typically won't refer to cyclone and anticyclone. I just wanted you to, when you see those terms, those refer to either low pressure systems moving upward, anticyclone referring to high pressure system moving downward. And where you see these, like a hurricane is an intense low pressure cell, and winds are being sucked into that. And because the direction of these winds, it kind of looks like this here. You can see that they're being kind of pulled in this kind of cyclone pattern.